We live in a world where objects have permanence. And we see cause, then effect. But a startling phenomenon is revealing that this is not how the universe works at the smallest scales of atoms and tiny particles. Albert Einstein argued it couldn't possibly be real.
Einstein was like a jack-in-the-box. Every day he'd pop up with a new challenge.
But after a century of disputes and discoveries,
the experiment is just beautiful.
We're using it to create revolutionary new technologies.
What we have here is a quantum playground.
We want to push this technology as far as possible.
It's perhaps the strangest concept in physics.
We're left with conclusions that make no sense whatsoever.
Yet it could be what forms the very fabric of our cosmos.
In the end, we just have this quantum mechanical world. There is no space anymore.
It's like being in Alice in Wonderland. Everything is possible.
Could it be real? It's Einstein's Quantum Riddle, right now on Nova. Is reality an illusion? Could something here mysteriously affect something there? A century of discoveries in physics reveals a strange, counterintuitive microworld of atoms and tiny particles that challenges our intuitive understanding of the world we see around us. It's known as quantum mechanics. This strange theory has enabled us to develop the remarkable technologies of our digital age. But it makes a very troubling prediction called quantum entanglement.
Entanglement is this very powerful but strange connection that exists between pairs of particles.
Even if they're very far apart, in a way they're always coordinated.
Nature's fundamental building blocks could be connected and influence each other instantaneously, as if the space between them doesn't exist. As if two objects can mirror each other without any apparent connection. Einstein called it spooky action at a distance. He rejected the idea and tried to prove it couldn't be real.
You could have situations where the cause and the effect happen at the same time.
But if entanglement isn't real, cutting-edge technologies could be in jeopardy.
Quantum computers, quantum encryption, they depend on entanglement being a fact in the world.
Underlying it all is a profound question. Do we live in Einstein's universe of common sense laws? Or a bizarre quantum reality that allows spooky connections across space and time? "300 miles off the coast of West Africa, on one of the Canary Islands, a team of physicists is setting up a remarkable experiment that will use almost the entire breadth of the universe. To settle the question, is the seemingly impossible phenomenon of quantum entanglement an illusion, or is it actually real? Leading the team is Anton Zeilinger.
So we are now going up the mountain towards the Roque de los Muchachos. So everything looks perfect today.
It's a precarious undertaking. They've got a short window on two of Europe's largest telescopes, Each one will simultaneously focus on a different quasar, an extremely distant galaxy emitting huge amounts of light from its core. This light will be used to control precise equipment that must be perfectly aligned to make measurements on tiny subatomic particles.
Fahren wir nach oben und unten, Charlie, okay?
Okay.
And if that isn't tricky enough, the weather on the mountain is notoriously unpredictable. The team needs perfect conditions for the experiment to work.
In the end, it could be running smoothly, or there need to be a couple of decisions made, you know, in an excited state in the last instant.
With the experiment finally set up, the team takes their positions. David Kaiser has worked on this experiment with his colleagues Jason Galicchio and Andy Friedman for 4 years. Coordinating it all is Dominic Rausch. The experiment is his thesis project, and it's been years in the making. But as darkness falls, temperatures on the mountain begin to drop.
Ja, Sie haben unsere Nummer und wenn es besser wird, werden wir angerufen.
Okay. Okay, großartig.
Ciao.
Okay, there's bad news. They have been told to leave the William Herschel because the road will be so dangerous, too dangerous, so they have to go down now. Yeah.
The next day, the team prepares for another attempt. They verify the equipment hasn't been affected by the weather. But now, the air is thick with clouds.
Here's the humidity at the various telescopes, and you see the humidity is 100%. So as long as this lasts, we can't do much.
The teams at both telescopes wait. But the clouds don't clear. All the preparation has come to nothing. Time on these huge telescopes is precious, and theirs has run out. This ambitious test of quantum entanglement must wait. Why are physicists so determined to put this bizarre aspect of quantum mechanics to the ultimate test? To explore the beginning of the story, David Kaiser has come to Brussels, the city that Albert Einstein traveled to in 1927, to attend a meeting about a new theory that described the microworld of atoms and tiny particles, quantum mechanics.
Quantum mechanics is one of those amazing intellectual achievements in human history.
For the first time, scientists were able to probe a world that was until then quite invisible to us. Looking at the world at the scale of atoms, 1,000,000 times smaller than the width of a human hair.
One way to think about the scales is that if you take an everyday object, like a soccer ball, and you enlarge that soccer ball so that actually you can see the individual atoms, you roughly have to make it the size of the Earth, and then move into that planet. Then you are in the world of atoms and particles.
It was the nature of fundamental particles which make up the world we see around us that Einstein had come to Brussels to discuss. And it was here that Einstein entered into a heated debate that would lead to the discovery of quantum entanglement. a concept that would trouble him for the rest of his life. David Kaiser has come to the place where it all began.
This is the original Solvay Institute building. Beautiful, grand building. And this is the place back in October 1927 where the 5th Solvay conference was held. This amazing week-long series of discussions on really what the world is made of, on the nature of matter and the new quantum theory. And these steps are the very steps on which this famous group photograph was taken. It's a collection of some of the most brilliant people in the world. Here in the front row, we see Albert Einstein and the great Marie Curie and Max Planck. In the back row, standing, the dapper Erwin Schrödinger, and these sort of brash 20-year-olds or mid-20s, Werner Heisenberg and Wolfgang Pauli.
These scientists were the pioneers of quantum mechanics.
I had a huge version of this photograph up on the wall as a poster in my college dorm room. My roommates had their favorite bands, and I had the 1927 Solvay conference, which says a lot.
This was one of the greatest meetings of minds in history. More than half were or would become Nobel Prize winners. Their experiments were showing that deep inside matter, tiny particles like atoms and their orbiting electrons were not solid little spheres. They seemed fuzzy and undefined.
So this group here, these were the folks who had just been plumbing deeper and deeper and deeper to find what they hoped would be a bedrock of what the world is made of. And to their surprise, they found things less and less solid as they dug in. This world was not tiny little bricks that got smaller and smaller. At some point, the bricks gave way to this mush. And what looked like solidity, solidness, in fact, became very confusing and kind of a whole new way of thinking about nature.
The theory of quantum mechanics presented at the meeting was strange. It said that a particle, like an electron, isn't physically real until it's observed, measured by an instrument that can detect it. Before it's detected, instead of being a solid particle, an electron is just a fuzzy wave, a wave of probability.
These objects, like electrons and atoms, when we describe mathematically their behavior, the only thing we can describe is the probability of being at one place or another.
It's like a wave of all those different possibilities. It's not that the electron is in one place or the other, we just don't know. It's that the electron really is a combination of every possible place it could be until we look at it.
Quantum mechanics only tells us the probability of a particle's properties, like location.
Laws of nature were no longer definite statements about what's going to happen next. They were just statements about probabilities. And Einstein felt, well, that's defeat. You're giving up on the heart of what physics has been, namely to give a complete description of reality.
For Einstein, the idea that particles only pop into existence when they're observed is akin to magic. It said he asked, "Do you really believe the moon is not there when you are not looking at it?" Outside of the formal setting of the conference, he challenged the most vocal supporter of these ideas, the great Danish physicist Niels Bohr.
Einstein would show up to breakfast at the hotel, and Niels Bohr would be there, and Einstein would present his latest challenge. Niels Bohr would sort of mumble and wonder and confer with his younger colleagues. They'd head off to the formal meeting at the Institute, and somehow every night by supper time, Bohr would have an answer. One of the observers said that Einstein was like a jack-in-the-box. Every day he'd pop up with a new challenge, and Bohr would flip this way and that, and then by supper have crushed that one, and it would start all over again.
To Bohr and his colleagues, quantum mechanics not only explained experimental results, its mathematics were elegant and beautiful. And since Einstein hadn't found flaws in their equations, they left the Solvay meeting feeling more confident than ever in their ideas. But Einstein didn't give up his conviction that quantum mechanics was flawed. And in his refusal to accept the weird implications of the theory, he would wind up uncovering something even weirder. In 1933, with the Nazi Party in power in Germany, Einstein chose to settle in America and took a position at the Institute for Advanced Study in Princeton, New Jersey. He recruited two physicists to help him, Nathan Rosen and Boris Podolsky. And in 1935, at afternoon tea, the three men spotted a possible flaw in quantum mechanics that would shake the very foundations of the theory. They noticed that the mathematics of quantum mechanics led to a seemingly impossible situation. Today, Robert Dijkgraaf is the director of the Institute.
Apparently Podolsky said, well, Professor Einstein, this is very important in your arguments showing that quantum theory is incomplete. So they got this very animated discussion, and what kind of happens still is now you have a bunch of scientists discussing, and at some point someone says, let's write a paper together. So they did.
Their paper, known today as EPR, argued that the equations of quantum mechanics predicted an impossible connection between particles, a seemingly magical effect. It would be like having two particles, each hidden under a cup. Looking at one mysteriously causes the other to reveal itself too, with matching properties. Quantum theory suggested this effect could happen in the real world. For example, with particles of light, photons. The equations implied that a source of photons could create pairs in such a way that when we measure one, causing it to snap out of its fuzzy state, the other mysteriously snaps out of its fuzzy state at the same instant, with correlated properties. The 1935 paper that described this effect has become Einstein's most referenced work of all. It has captivated generations of physicists, including Anton Zeilinger.
The Einstein-Podolsky-Rosen paper fascinated me, and I had to read it at least 5 or 6 times until I finally understood what goes on. And then it didn't let me go again.
Another way to think of the paired particles is to imagine a game of chance that's somehow rigged.
Suppose I had a pair of quantum dice. I put these 2 quantum dice in my little cup, throw them. I look at them, they show the same number, 6. I put them again in the cup, throw them again. Now they both show 3. I put them in again, throw again. Now they both show 1. Point now being, what I see here is, I see 2 random processes, namely each die showing some number, but these 2 random processes do the same. That's really mind-boggling.
How could 2 particles act in unison, even when they're separated from each other?
Essential to the EPR argument is that these particles can be separated at an arbitrary distance. One could be here at Princeton, one could be in the Andromeda galaxy. And yet, according to quantum mechanics, a choice to measure something here is somehow instantaneously affecting what could be said about this other particle. You can't go from Princeton to Andromeda instantly. And yet that, they argued, is what the equations of quantum mechanics seem to imply. And that, they said, so much the worse for quantum mechanics. The world simply can't operate that way.
For Einstein, this strange effect conflicted with the most basic concept we use to describe reality: space. For him, objects, particles, everything that exists is located in space. Space, together with time, was the key ingredient in his theory of special relativity, with its famous equation E equals mc squared.
Einstein, of course, was the master of space-time. He thought that if something happened here, that shouldn't immediately and instantaneously change something that is going on over there, the principle of locality, as we currently call it.
For Einstein, it's simply common sense that if objects are separated in space, for one to affect the other, something must travel between them. And that traveling takes time. Quantum particles acting in unison could be explained if they were communicating. One particle instantly sending a signal to the other, telling it what properties it should have. But that would require a signal traveling faster than the speed of light, something Einstein's theory of special relativity had proven impossible. And it would mean the particles were fuzzy and undefined, until the moment they were observed. Instead, Einstein thought the particles should be real all along. They must carry with them a hidden layer of deeper physics that determines their properties from the start. Almost the way that magic tricks, while appearing mysterious, have a hidden explanation. But this hidden physics was missing from quantum theory. So Einstein, Podolsky, and Rosen argued that quantum mechanics was incomplete.
Podolsky was very enthusiastic about this project. In fact, he was so enthusiastic that he ran to the New York Times and told them the news. So Einstein was really upset with Podolsky, and apparently he didn't speak to him anymore.
When Niels Bohr heard of Einstein's paper, he wrote an obscure response, arguing that one particle could somehow mysteriously influence the other. This seemingly impossible phenomenon became known as quantum entanglement. But Einstein dismissed it as spooky actions at a distance. No one could think of an experiment to test whether Einstein or Bohr was correct. But that didn't stop physicists and engineers from making use of quantum mechanics to do new things.
In the 30s and 40s, the debate around the EPR paper sort of dies down, but quantum theory actually takes off. The mathematics leads to all kinds of amazing developments.
Entanglement aside, the equations of quantum mechanics enabled the scientists of the Manhattan Project to develop the atomic bomb. And in the years after the Second World War, researchers at Bell Labs in New Jersey used quantum theory to develop one of the first lasers.
In our laboratories, men experiment with a light once undreamed of in the natural world.
And build small devices that could control the flow of electricity, transistors.
It's destined to play a vital role in your future, your electronic future.
Transistors became the building blocks of the burgeoning field of electronics. Computers, disk drives, the entire digital revolution soon followed, all made possible by the equations of quantum theory. Yet Einstein's questions about entanglement and what it implied about the incompleteness of quantum mechanics remained unanswered until the 1960s, when a physicist from Northern Ireland made a remarkable breakthrough. John Bell.
Bell was a very talented young physics student, but he quickly grew dissatisfied with what he considered almost a kind of dishonesty among his teachers.
Bell insisted that Einstein's questions about quantum mechanics had not been addressed.
He got into shouting matches with his professors. Don't tell us that Bohr solved all the problems. This really deserves further thought.
Quantum mechanics has been fantastically successful, so it is a very intriguing situation that at the foundation of all that impressive success, there are these great doubts.
It's a very strange thing that ever since the 1930s, the idea of sitting and thinking hard about the foundations of quantum mechanics has been disreputable among professional physicists. When people tried to do that, they were kicked out of physics departments. And so for someone like Bell, he needed to have a day job doing ordinary particle physics. But at night, hidden away, he could do work on the foundations of quantum mechanics.
Bell became a leading particle physicist at CERN in Geneva, but he continued to explore the debate between Einstein and Bohr. And in 1964, he published an astonishing paper. Bell proved that Bohr's and Einstein's ideas made different predictions. If you could randomly perform one of two possible measurements on each particle and check how often the results lined up, the answer would reveal whether we lived in Einstein's world, a world that followed common sense laws, or Bohr's, a world that was deeply strange and allowed spooky quantum connections.
We now know with hindsight this was one of the most significant articles in the history of physics, not just the history of 20th century physics, in the history of the field as a whole. But Bell's article appears in this, sort of out-of-the-way journal. In fact, the journal itself folds a few years later. This is not central to the physics community. It's sort of dutifully filed on library shelves and then forgotten. It literally collects dust on the shelf.
A few years later, completely by chance, a brilliant experimental physicist stumbled upon Bell's article.
I thought this is one of the most amazing papers I had ever read in my whole life. And I kept wondering, well, gee, this is wonderful, but where's the experimental evidence?
John worked on Bell's theory with fellow physicist Abner Shimoni, and at the University of California, Berkeley, started work on an experiment to test it. He had a talent for tinkering in the lab and building the parts he needed.
I used to rummage around here and scavenge and dumpster dive for old equipment.
He knew where to find hidden storage rooms like this, which he could raid to salvage spare parts for his experiments.
And this was a power supply for diode lasers. That looks like something I built. Here's a picture of the experiment I did. I had more hair in those days. Here's another picture. This is Stu Friedman, worked on it with me.
Piece by piece, John Clauser and Stuart Friedman constructed the world's first Bell test experiment. They focused a laser onto calcium atoms, causing them to emit pairs of photons that the equations of quantum theory suggested should be entangled. They recorded whether or not the photons passed through filters on each side and checked how often the answers agreed. After hundreds of thousands of measurements, if the pairs were more correlated than Einstein's physics predicted, they must be spookily entangled.
We saw the stronger correlation characteristic of quantum mechanics. We measured it, and that's what we got.
The outcome was exactly what Bohr's quantum mechanics predicted. The experiment appeared to show that the spooky connections of quantum entanglement did exist in the natural world. Could it be that the great Albert Einstein was wrong? Remarkably, The first people to react to this extraordinary result were not the world's leading physicists.
Ronald Reagan's definition of a hippie was someone who dresses like Tarzan, has hair like Jane, and smells like cheetah.
A small group of free-thinking physicists at the heart of San Francisco's New Age scene got in touch with John.
They call themselves the Fundamental Physics Group. They spelled physics with an F. Some members would experiment with psychedelic drugs. I mean, they were kind of in the flow of the kind of hippie scene. And that group was just mesmerized by the question of entanglement.
The idea was just to discuss fringe subjects with an open mind, and I thought, sure, that's kind of what I do. They were doing their best to link Eastern mysticism with quantum entanglement. They sold a lot of popular textbooks. There were a lot of followers.
Their books became bestsellers, like The Tao of Physics, which highlighted that Eastern philosophy and quantum entanglement both described the deep connectedness of things in the universe.
It was the great cosmic oneness.
The group held meetings at the iconic Esalen Institute.
It was a marvelous, beautiful place where they would discuss all of these ideas. It was right on the Pacific coast with the overflow from the hot tubs cascading down the cliffs into the Pacific Ocean. To my knowledge, no useful connections to Eastern mysticism were ever discovered by the group. But it was fun.
The Fundamental Physics Group may not have uncovered the secrets of cosmic oneness, but in seeing entanglement as central to physics, they were decades ahead of their time. "40 years later, cutting-edge labs around the world are now racing to harness quantum entanglement to create revolutionary new technologies like quantum computers.
In our everyday computers, the fundamental unit of computing is a bit, a binary digit, 0 or 1. And inside the computer, there's all these transistors which are turning on and off currents. On is 1, off is 0, and these combinations lead to universal computing. With a quantum computer, you start with a fundamental unit that's not a bit, but a quantum bit, which is not really a 0 or a 1, but it can be fluid.
A quantum bit makes use of the fuzziness of the quantum world. A qubit, as it's known, can be 0 or 1, or a combination of both. A particle or tiny quantum system can be made into a qubit. And today, it's not just pairs of particles that can be entangled. Groups of qubits can be linked with entanglement to create a quantum computer. The more qubits, the greater the processing power. At Google's quantum computing laboratory in Santa Barbara, the team has recently succeeded in creating a tiny chip that holds an array of 72 qubits. The task for researcher Marissa Giostina and her colleagues is to send signals to these microscopic qubits to control and entangle them.
Mounted on the underside of this plate, we have the quantum processing chip itself. In essence, a quantum playground, you could say. Each qubit is a quantum object that we should be able to control at will. Thinking about it as the faster version of that PC over there would be a great slight to this. It can be much more than that.
By using entangled qubits, quantum computers could tackle real-world problems that traditional computers simply can't cope with. For example, a salesman has to travel to several cities and wants to find the shortest route. Sounds easy, But with just 30 cities, there are so many possible routes that it would take an ordinary computer, even a powerful one, hundreds of years to try each one and find the shortest. But with a handful of entangled qubits, a quantum computer could resolve the optimal path in a fraction of the number of steps. There's another reason teams like Marissa's are racing to create a powerful quantum computer: cracking secret codes. In today's world, everything from online shopping to covert military communications is protected from hackers using secure digital codes, a process called encryption. But what if hackers could get hold of quantum computers?
A quantum computer could crack our best encryption protocols in minutes, whereas a regular computer or even a supercomputing network today couldn't do it, given months of time.
But while quantum entanglement may be a threat to traditional encryption, it also offers an even more secure alternative: a communication system that the very laws of physics protect from secret hacking. Researchers in China are leading the way. Here in Shanghai, at the University of Science and Technology, Jianwei Pan runs a leading quantum research center. His teams are working to harness the properties of the quantum world. They can send secret messages using a stream of photons in a system that instantly detects any attempt to eavesdrop. Jianwei's team has created a network of optical fibers more than 1,000 miles long that can carry secure information from Beijing to Shanghai. It is used by banks and data companies. But there's a limit to how far quantum signals can be sent through optical fibers. To send signals further, Jianwei's team launched the world's first quantum communication satellite. Above Earth's atmosphere, there are fewer obstacles, and quantum particles can travel much further. Each night, teams on the ground prepare to track the satellite across the sky. Laser guidance equipment locks on and allows signals to be sent and received. The team aims to use this equipment to create a new, secure communication system using quantum entanglement. The satellite sends entangled photons to two users. An eavesdropper could intercept one of the entangled photons, measure it, and send on a replacement photon. But it wouldn't be an entangled photon. Its properties wouldn't match. It would be clear an eavesdropper was on the line. In theory, this technique could be used to create a totally secure global communication network.
So the next step is we will have ground station, for example, in Canada, and also in Africa and many countries. So we will use our satellite for the global quantum communication. We want to push this technology as far as possible.
These are the first steps in creating a completely unhackable quantum internet of the future, made possible by quantum entanglement. But there's a problem. What if quantum entanglement, spooky action at a distance, isn't real after all? It could mean entangled photons are not the path to complete security. The question goes back to Clauser and Friedman's Bell test experiment. In the years after their pioneering work, physicists began to test possible loopholes in their experiment. Ways in which the illusion of entanglement might be created, so the effect might not be so spooky after all. One loophole is especially hard to rule out. In modern Bell test experiments, devices at each side test whether the photons can pass through one of two filters that are randomly chosen, effectively asking one of two questions and checking how often the answers agree. After thousands of photons, if the results show more agreement than Einstein's physics predicts, the particles must be spookily entangled. But what if something had mysteriously influenced the equipment so that the choices of the filters were not truly random?
Is there any common cause deep in the past, before you even turn on your device, that could have nudged the questions to be asked and the types of particles to be emitted? Maybe some strange particle, maybe some force that had not been taken into account, so that what looks like entanglement might indeed be an accident, an illusion. Maybe the world still acts like Einstein thought.
It is this loophole that the team at the High Altitude Observatory in the Canary Islands is working to tackle. With quantum mechanics now more established than ever, they're determined to put entanglement to the ultimate test and finally settle the Einstein-Bohr debate beyond all reasonable doubt. The team is creating a giant version of Clauser and Friedman's Bell test, with the entire universe as their lab bench. In this cosmic Bell test, the source of the entangled particles is about 1/3 of a mile from each of the detectors. The team must send perfectly timed pairs of photons through the air to each side. At the same time, the telescopes will collect light from two extremely far-off, extremely bright galaxies called quasars. These are among the brightest objects in the sky, emitting light in powerful jets. Random variations in this light will control which filters are used to measure the photon pairs. And since the quasars are so far away, the light has been traveling for billions of years to reach Earth. It makes it incredibly unlikely that anything could be influencing the random nature of the test. If the experiment is successful, the team will have tackled the loophole and shown that quantum entanglement is as spooky as Bohr always claimed. Dominic and Jason are at one telescope.
Hello, Anton.
Anton is at the other.
Wir hatten gerade schon den Quasar im Field of view oder in der Iris.
Mit der Quelle funktioniert es auch.
Ja, Quelle funktioniert, der Kontrast ist super. Läuft.
Das Licht jetzt.
Okay. Ciao.
With clear skies finally overhead, the huge telescopes awaken. Poised to collect light from distant quasars.
Moving.
Dominic, is this a Darkon level or is it a Field
Arrive.
Darkon level.
Okay, this is good.
So we're doing everything at once now. So the guys for the links are setting the state of the entangled photon pair. We try to acquire the quasar. We're just centering it and making the field of view as small as possible to be sure that we only have the quasar.
Okay.
It's guiding now?
Yes, let's wait one more image.
Okay.
Of this one.
All right.
Great.
Yes.
Okay.
Yeah, ich hab's gehört.
It looks like 90, let's say 91 to be conservative, of purity.
With the telescopes now locked on to two different quasars, the team begins to take readings.
Red counts 12,000, blue counts 7,000.
We do the full cosmic bell test.
What?
Yeah, we're doing a full cosmic bell test.
It's working. Light from the quasars is selecting which filters are used to measure the entangled photons.
It is exciting. It is, now we do have a test, but it's not clear what the outcome will be.
Going. All right.
Everything's exactly the same. Beautiful, perfect. Yeah.
2 months later, back in Vienna, the team analyzes the experimental data.
This might take a second. The numbers look really great, and it is extremely pleasing to see that all this works so nice. We clearly see correlations that correspond to quantum mechanics.
The results show entanglement. And since the light from the quasars controlling the test was nearly 8 billion years old, it's extremely unlikely that anything could have affected its random nature. This remaining loophole seems to be closed.
The experiment we did is just fantastic. The big cosmos comes down to control a small quantum experiment. That in itself is beautiful.
You know, honestly, I still get chills. I mean, when I realized what our team was able to do in this intellectual journey that stretches back to the early years of the 20th century, there's hardly any room left for a kind of alternative Einstein-like explanation. We haven't ruled it out, but we've shoved it into such a tiny corner of the cosmos as to make it even more implausible for anything other than entanglement to explain our results.
Accepting that entanglement is a part of the natural world around us has profound implications. It means we must accept that an action in one place can have an instant effect anywhere in the universe, as if there's no space between them. Or that particles only take on physical properties when we observe them. Or we must accept both.
We're left with conclusions about the universe that make no sense whatsoever. Science is stepping outside of all of our boundaries of common sense. It's almost like being in Alice in Wonderland, right, where everything is possible.
It was first seen as an unwelcome but unavoidable consequence of quantum mechanics. Now, after nearly a century of disputes and discoveries, spooky action at a distance is finally at the heart of modern physics. At the Institute for Advanced Study, where the concept of entanglement was first described, researchers are now using it in their search for a single unified theory of the universe, the holy grail of physics. Einstein's theories of special and general relativity perfectly describe space, time, and gravity at the largest scales of the universe, while quantum mechanics perfectly describes the tiniest scales. Yet these two theories have never been brought together.
So far, we've not yet had a single complete theory that is both quantum mechanical and reproduces the prediction of Einstein's wonderful theory of general relativity. Maybe the secret is entanglement.
What if space itself is actually created by the tiny quantum world? Just like temperature, warm and cold consists simply of the movement of atoms inside an object. Perhaps space, as we know it, emerges from networks of entangled quantum particles. It's a mind-blowing idea.
What we are learning these days is that we might have to give up that what Einstein holds sacred. namely space and time. So he was always thinking, well, we have little pieces of space and time, and out of this we build the whole universe.
In a radical theory, known as the holographic universe, space and time are created by entangled quantum particles on a sphere that's infinitely far away.
What's happening in space, in some sense, all described in terms of a screen outside here. The ultimate description of reality resides on this screen. Think of it as kind of quantum bits living on that screen. And this, like a movie projector, creates an illusion of the three-dimensional reality that I'm now experiencing.
It may be impossible to intuitively understand this wild mathematical idea, but it suggests that entanglement could be what forms the true fabric of the universe.
The most puzzling element of entanglement, that somehow 2 points in space can communicate, becomes less of a problem because space itself has disappeared. In the end, we just have this quantum mechanical world. There is no space anymore. And so in some sense, the paradoxes of entanglement, the EPR paradox, disappears into thin air.
Truly understanding quantum mechanics will only happen when we put ourselves on the entanglement side, when we stop privileging the world that we see and start thinking about the world as it actually is.
Science has made enormous progress for centuries by sort of breaking complicated systems down into parts. When we come to a phenomenon like quantum entanglement, that scheme breaks. When it comes to the bedrock of quantum mechanics, the whole is more than the sum of its parts.
The basic motivation is just to learn how nature works. What's really going on? Einstein said it very nicely. He's not interested in this detailed question or that detailed question. He just wanted to know what were God's thoughts when he created the world.